So we were looking at addressing as part of the IP protocol, but first let me see how much you remember. So we saw that flat addressing is a no-no. We need structure as part of the IP address to handle scalability. Accordingly, we divided an IP address into a network portion as well as a host portion. That way, routers can only maintain one entry corresponding to a network and not maintain individual host entries. We also saw this addressing was divided into classes A, B, C, D, E, but D and E are special addresses. So ABC is what is relevant, and this was done to handle different network sizes. So this should take care of things. What can potentially go wrong? At the beginning, nothing really went wrong, but as internet grew and as more and more networks got added, this was found not to be scalable. Can you think of why? What is wrong with this classful addressing? So here is the problem. Remember that a network part uniquely identifies a physical network. Suppose you have a network with just two hosts. Now what class address will you give such a network? And what do you think is the efficiency of your address space? So let me clarify something here. There is an IP address. This is an address given to a host, which is 32 bits. And then there is a class address, for example, a class B address. An example of this could be 190.23.**, where the network portion is the 16 bits. Such a class B address could be allocated to a given network where the hosts will take these portions where you have 2 to the power of 16 combinations, and you can assign these addresses to the different hosts. So a class B address corresponds to a block of IP addresses. So this is something to keep in mind. Now going back to the question, for a network with just two hosts, what class address will you give and what is the address space efficiency? Now if you have this network with just two hosts, it still needs a class C address because class B and class A support a lot more hosts. Class C supports the least number of hosts, so you need to give it a class C address. And now what is the efficiency? One class C address, because it has 8 bits corresponding to the host part, can support 2 to the power of 8 hosts. So the efficiency is, if you allocate this to this particular network, is you're using 2 addresses out of 2 to the power of 8. That means you have an efficiency of 0.7%, very low efficiency. What if you have a network with 256 hosts? What class address will you give? And what is the efficiency of this, the address space? Well, you need to give a class B address because class C will not support this. And here is, you can potentially support 2 to the power of 16 hosts, but you're only using 256 host addresses. So the efficiency is even worse of only 0.4%. So we must have been quite happy. 32 bits means we can support 2 to the power of 32 hosts, which roughly translate into 4 billion hosts. But when you are allocating the addresses, there is so much inefficiency. You cannot even reach this number. Among class A, B, C addresses, which address do you think will be in most demand? The number of organizations that support 2 to the power of 24 hosts, whereby they need a class A address, are going to be very few because these are really big organizations. So most organizations will fall in the category of either class C or class B, but often when an organization, even if it has only let's say 150 hosts, while it can manage with a class C address, would ideally want a class B address because in the future this organization can grow and then it can't say I want a class B address now. So it's better for an organization, keeping in future needs in mind, to ask for a class B address. Given this, roughly when do you think the address space will run out? By which I mean you do not have any addresses to give to networks. As people keep asking for class B addresses, once you're out of class B addresses, that's it. You're out of the addresses to hand out. And there are Class B addresses, the number of such addresses are 2 to the power of 14, which roughly translates into 16,000. Even though you can potentially support 4 billion hosts, once this address space runs out, you are in trouble. And that's precisely what has happened as internet grew. So we need to solve this problem of address assignment inefficiency, but the biggest challenge is you still need to work within the IP framework where you are having to use 32-bit IP addresses. Well, you could say I will go for more number of bits for the IP addresses. So that's what IP version 6 did. But this was already deployed, the IP version 4, and you cannot say I'll quickly transition to IP version 6 because there was a lot of investments in the routers, host, and the software that these routers and hosts run. So you can't make changes instantaneously. It will take some time. Within this, you still need to solve the scalability problem. How to solve this within the IP framework? So what are your thoughts? How will you solve this problem? So here is some yarn for you to help solve the problem. The gem cannot be polished without friction. No man perfected without trials. So the IP protocol, you cannot perfect it without such problems. And people went on to solve this problem. So it's feasible. And the attitude to solve this problem is captured by this quote. You see a mousetrap, I see free cheese and a dash challenge. I will let you fill these entries up. This is a censored word. So tell me, given 32 bits and this class A, class B, class C addressing, and the fact that once you are out of class B, you are out of addresses, how will you solve this scalability problem? That is the address assignment inefficiency problem. To set the context, let's look at a very specific example. Suppose there is an organization. It has 30 different physical networks, and each networks roughly there are about 2,000 hosts. So the first question is, in the original IP, how many addresses will you give to this particular organization and what class of addresses will you give? Don't think of the solution I asked for earlier. In the original IP, what would you do? Well, there are 30 different physical networks. That means you will need to allocate 30 addresses. Since each has 2,000 hosts, a class C address will not suffice. You need to give class B addresses. So you will allocate 30 class B addresses, and the efficiency here is you're only supporting 2,000 hosts out of 2 to the power of 16 hosts. That is an efficiency of only 3%. You have wasted a lot of addresses. Do you think we can manage with one class B address? Well, the calculation says yes, because you have 2 to the power of 16 hosts you can support as part of class B, that is 65,536 hosts, and the number of hosts that are part of this organization is 30 into 2,000, that is 60,000, which is less than 65,536. But how do we allocate this class B address to these 30 different physical networks? The answer is not difficult. You have seen the solution before. Simple, add another level of hierarchy, basically network portion and host portion. So what you do is you take the host portion and subdivide it into two other parts. One corresponds to subnet portion, another corresponds to the host portion. For example, in the earlier example, we have 16 host bits divided into 5 subnet bits. So 5 subnet means you can support 32 physical networks, and 11 host bits can support 2048 hosts. So we have, in fact, we can support more than 30, we can support 32, and we can support more than 2000, we can support 2048 hosts. And now what you do is you allocate network addresses where the network portion is no more 16 bits, but it is 16 plus 5 bits, that is equal to 21 bits. A given host address, here I am talking about IP address, takes on this particular form, a.b.c.d/x, where x is the number of bits in the network portion of the address. So for example, if this is the IP address of a host, you specify the number of bits that correspond to the network portion of the address as /21, This is also often represented by a mask, which is saying that 255 means this is 8 ones. Again, this 255 refers to 8 ones, and this 248 refers to 1, 2, 3, 4, 5 ones followed by 3 zeros. So this 8 bits are represented in this particular fashion. So this is saying that there are 21 ones followed by the remaining zeros. This host belongs to a specific network. What is the network number corresponding to that particular network? How would you represent it? Maybe a bit tricky, but give it a try. So basically this one will translate to 190.23.8.0/21. So this is the network number. How did this number arise? So look at 12. This translates to 00001100. Now I have to look at the first 5 bits, which is equal to this. So this 190.23.0001000 is the network ID. This portion will correspond to the host portion. So the host will take values in this range. So if you were to translate this, this is what? This corresponds to 8, this corresponds to 0. So the network portion is saying this is the network portion of it. The first 21 bits is what you're looking at. Now if you want to assign this address to a given host, you can do it using the ifconfig command in Linux. So it will be ifconfig 80 the IP address, and then you use this net mask to indicate that the network portion is now not 16 bits, even though this is a class B address, but rather 21 bits. So here this is a mistake, it should be 248. So this is the net mask. Now if you want to determine what the subnet number of the host is, as we have done here, all you need to do is do a bitwise AND between the IP address and the subnet mask, and you will get the subnet number of the host. In other words, the network to which this host belongs to. So a point to note here is that all the hosts on a given physical network will have the same subnet number and the mask. So addressing our original problem where we were given one class B address, let's suppose that this class B address is this, which I am representing in this particular fashion because it's class B address. The network portion corresponds to the first 16 bits, and this is set equal to 190.23. Now the host portion is this remaining 16 bits. So this is what I'm doing. I'm creating 32 subnets, even though the organization has only 30. In case it grows in the future, it can use the remaining subnets. But I'm dividing this portion into the host portion into 5 bits of subnet portion and 11 bits of the host portion. 11 bits of the host portion. So these 5 bits, I use different combinations ranging all the way from 00000 all the way till 11111 to generate 32 subnets, and this is the subnet number corresponding to each. You do this calculation as we have done earlier, you will be able to figure out these numbers, and within a given subnet number I'll use the host portion and again enumerate all combinations of 2 to the power of 11 to arrive at this address block. If you notice one thing here, I have not included the host portion that corresponds to all zeros, nor the host portion that corresponds to all ones. Typically the host portion that corresponds to all zeros matches the subnet number. So typically you don't want to assign an IP address to a host which matches the subnet number. And similarly, the host portion that corresponds to all 1 is typically the broadcast address in that particular subnet. So you don't want to use that either. So whatever is remaining, that is 2 to the power of 11 minus 2, is what is allocated to the individual hosts. Now what is the entry that routers that are far away from this particular organization will maintain to route traffic to this particular organization? You can have one single entry corresponding to this. Because this entire organization was allocated a class B address, this is what it was allocated, so they just maintain this entry. So once traffic comes to this organization, the routers within the organizations are going to handle the routing. So these will maintain lot more entries corresponding to the different subnets. We will see an example shortly that will make this clear. So let's see the forwarding action at a router now. Now routers get packets with destination address as part of the IP header. Let's say the destination address is D, and each router also has a forwarding table. This forwarding table now maintains 3 entries. It will specify what the network number is, what is the mask, and what interface you need to send packets on. So what you do is, whenever you get a packet with the destination D, you take the first entry, you do an AND between this destination and the mask, and then see whether it matches this network number. If it matches the network number, you will look at the interface and thereby forward this on that particular interface. Now if it didn't match, you move on to the next entries, and you keep on doing till some entry matches as part of your forwarding table. Remember, forwarding tables will always have a default entry which says to forward it to some other router, or in case there are no entries, you will just have to discard the packet. So this example puts everything together. So here is the organization. It has many subnets. I've just indicated 3. There are others going in this direction through via router 2. So this network has been given this particular subnet number. Notice that you have to look at 21 bits to determine what the network portion is. Similarly, this network has been given this subnet, and this network has been given this subnet, and there are other networks also. Now look at router R1. So this is the routing table at R1, that is the forwarding table. Let me be consistent here. And it has these entries. So whenever R1 receives a packet, it is now going to do an AND between the destination address and mask. If it corresponds to this, it knows it can reach via interface 0. If it corresponds to this, it knows it can reach via interface 1. And for any other, because this is part of this organization where the mask is 16, it can reach the other networks as part of its organization via R2. So it is going to maintain R2. And as I mentioned, most routers have a default network that connects to the rest of the internet. So for any other packet where it is outside this organization, it is saying go to R2. And I had mentioned earlier also, some router that is somewhere in the internet here will just maintain one entry 190.23.0.0/16 to represent this entire organization. When I talked about forwarding in a previous video and showed this routing table, I mentioned that this is a class A address, but mask, I said, is looking at 16 bits. Now I think it should be clear why you are looking at 16 bits of a class A address. So are we done solving the scalability problem? Unfortunately, no. So here is another problem as captured by this specific scenario. Now we have an organization that has only one physical network, but it has 4,000 hosts. Based on whatever you have learned so far, the original IP scheme as well as subnetting scheme and so on and so forth, what network address will you give this particular organization? Subnetting is not going to help here. You need to give it a class B address, leading to an efficiency of only 6%. Now, how would you improve this efficiency? With that question in mind, I wish I could provide popcorn and soda, but you're on your own. Still remember the problem, or you forgot? Let me reiterate. So here we have an organization that has only one physical network, but with 4,000 hosts. Subnetting doesn't help, so we have to give this a class B address that leads to very poor efficiency. Now, how do we solve this particular problem? How about assigning multiple class C addresses? So that way you can maintain high efficiency. So how many class C addresses do you need to allocate for this? 16, right? Where each class C address caters to 2 to the power of 8 hosts, roughly. Is there any problem with this approach, or are we done? Well, we are never done. So the problem with this is now for one organization, you have 16 entries in the routing table. So this is again going to lead to scalability issues where you are representing one organization by 16 entries. This will not do. So what can we do? Can you think of a solution? You should be able to think. It may be a bit tricky, but we have seen similar principles in practice before. Simple solution: assign multiple contiguous class C addresses and then you aggregate. What do I mean by this? So for this specific case, you take this address range. So this class C addresses that are in this range where the top 20 bits in this range are the same. This corresponds to 0001. And then designate a 20-bit network number. So what would you advertised as the organization's network number? Right? 222.7.16/20. So this is what you would advertise. So a router somewhere in the internet will know that to reach this organization, it will just maintain one single entry. So this solution goes by the name supernetting. Earlier was subnetting, this is supernetting. So this is a quick summary of what we have seen. In subnetting, one class address is shared among many physical networks. In supernetting, multiple class addresses are shared among one physical network. In supernetting, this physical network I also at times will refer to as autonomous system, basically an organization managing a particular network. We refer to it as an autonomous system. So the conclusion across both of this is that the network portion can take on any length. What all lengths do you think the network portion can take, given that we do subnetting as well as supernetting? Well, it can take on any value between 2 to 32. 2 because the class A, the first bit is always fixed at 0. 32, just like a one-man army, you can have a one-host network, in which case you have to, the network mask will have to specify all the 32 bits. So this leads to what is called a classless inter-domain routing. So there are no more classes A, B, C, D, E, because the network portion can be of any length. So we use a new notion to represent network numbers. This is called IP prefixes. So the address block is represented in this particular fashion, where A is the address prefix and X is the prefix length. And this X, as I mentioned, can take on values from 2 till 32. X is also represented as a network mask, where that /21, for example, is represented like this. To concretize, this 222.7.16-20, where the mask corresponds to this, represents addresses in the range from all the way here to here. So a router that maintains this entry will match the destination address in an IP packet. If it falls anywhere within this range, it is going to forward it on the interface that is specified by this particular entry. A reiteration of what I said. So routers are now going to do a prefix match. Basically, they will ask this question: does the destination address fall in the range of addresses captured by the prefix? If so, send it out on the interface specified by this particular prefix. So this works great if the internet topology is a tree where the shortest path between networks is unique. But unfortunately, the internet topology is a graph, mainly because many networks at times are multi-homed for fault tolerance or load balancing purposes. Again, let me explain what I mean by multi-homing. In the previous example, the 190.23.8.0/21 network was connected to the internet via R2, which is going via R1. Now it's possible that I could also directly connect it to the internet via some other router R6. So this network is now multi-homed. Now it can access the internet both via R1 as well as R6. As mentioned, you do this mostly for fault tolerance and redundancy purposes. Now, if you did something like this, now you will have two matching prefixes as part of a router's forwarding table somewhere in the internet core. One corresponding to this and another corresponding to this. This is what maybe R2 will advertise and this is what R6 will advertise. Now, this address belonging to this particular network is going to match both these prefixes. Now, who do you send this packet to? Simple rule, go with the longest prefix match. So that's what you implement. Now, if you look at the task of forwarding, now we have to do the longest match between a destination IP address and a variable length prefix as part of the forwarding table. And when we covered the router design, you want to do it extremely fast. So there's a lot of research that happens in this space. We are not going to cover all that. Now, are we done with addressing? Not quite. We are done as far as this video is concerned. There are more issues we will cover as part of other videos. So here is a summary of what we have seen so far. We found that the class-based addressing is not scalable. So to address the scalability issues, we looked at two solutions. One is subnetting, where we share a single class address among multiple physical networks. Another is supernetting, where we share multiple class addresses on a single network. So this has led to what is called a classless addressing scheme, where we employ the longest prefix match as part of router, and this is what is widely used now. So we will see other issues with addressing and solutions for the same in other videos.